We're going to go through a variety of different sample problems just to make certain that we can work through things. Our algebra, so I've got x to the 15 equals 1325. Solving an equation. Now we're dealing with money. We're not going to have any negative negative outcomes. We don't need to worry about the plus or minus when we're taking a root. Solving equations. What I see, our variable is in the base. We've got a number in the exponent. When we have a number in the exponent, we take a root to cancel that out. And you can't see that, can you? Nope. Bring it down. There we go. Number in the exponent. Take a root to solve. Now I'm going to be using rational exponents. I'm going to hopefully be using a marker that's not completely dead. X to the 15th, we're going to raise both sides to an exponent to cancel that out. So I've got x to the 15. I'm going to raise that whole side to the 1 over 15. Remember our properties of exponents. We'd have an exponent raised to an exponent. We would multiply 15 multiplied by 1 over 15. Cancels. So I raise both sides to the 1 over 15. On the left side, that cancels. On the right side, I can get it in the calculator. And you see that? You cannot see that. Let's see, can we lighten that up? It's a little bit better. It is what it is. So 1325 to the 1 over 15, and okay, there we go. 1.615. We'll round to 3 decimal points. Fantastic. Old news. Good. Comments, questions, concerns. We see a number in the exponent. We use a root to pull the exponent out to cancel that. Solving. This is going to show up in our compound interest. Building. Order of operations. Work from the outside in. Order of operations, working from the outside in. We first got to get rid of the 36, then we'll get rid of the plus 1. Anytime we have a number in the exponent, it's the 1 over that exponent to solve. So I'd have 1 plus y to the 36. Different brackets don't mean anything, just so I can group those to the 1 over 36. 1.31, 1 over 36. I can pop that in the calculator, get something. On the left side, 36 exponent to 1 over 36 exponents. Multiply 36 times 1 over 36 cancels. That would leave us with just 1 plus y. On the right side, .0075. Order of operations, work from the outside in. We've got the outermost piece, get rid of the innermost, subtract 1. This kind of thing shows up when we work with compound interest with the other formulas that we're going to be using. So right now it's reminder of our algebra. Numerical value in the exponent, we take a root to eliminate that. I'm going to use that fractional exponent. The 1 over the current exponent will solve for the base. Comments, questions, concerns? Because now I'm going to change things. If the exponent is not a numerical value, if instead our exponent is the variable, I'm just going to rewrite that so it shows up a little bit better. Variable is the exponent. Oh no. Well, if we do 1.025 to the x and we raise that to the 1 over x, we would have 3 to the 1 over x. So we'd have 1.025 equals 3 to the 1 over x. Oh no, we've got, the variable is still in the exponent. Well, if I raise that to the 1 over x, then it would be 1.025 to the 1 over x would be 1.025 to the x equals, we're back at the beginning. So it's not the case where we raise it to the 1 over. When we have our variable in the exponent, that's our logarithm. Now, last year, you worked with different bases. I'm going to keep everything base 10. So no other bases, none of the adding, subtracting, combining, working with logs. Did that last year. This year, we're going to focus on just using logs as a tool to solve equations. Anytime we have a variable in the exponent, what we're going to do is we're going to take a log of both sides. So I'm going to use log base 10. That's just a button in the calculator. So it's going to be log of 1.025 to the x equals log of 3. So taking the log of both sides, it's like taking the square root of both sides. We are doing an operation to both sides. What happens here, we've got an exponent inside of a log. This was one of those properties of logarithms. An exponent inside of a log comes out front, turns that into multiplication. So this turns into now x multiplied by log 1.025 equals log 3. No more variable in the exponent, it's multiplication. Now what that does for us, log 1.025, that's just a number. So I can type that into the calculator, log 1.025. I get some decimal. So this is actually 0.0107x equals log of 3. I can just type that into the calculator. I am using the log button. There's log, there's ln immediately below it. I'm just using log, doesn't matter. So log 3, 1.099. So 1.099. That's just some number. Now we've got a decimal equation. That's multiplication. The opposite of multiplication, we divide. I'm going to write it out. .71. Anytime we see the variable in the exponent, we log both sides. That's how we need to use log. So all the stuff that we had from Algebra 2 doesn't get more complicated than this. There might be just some equation stuff that we have to work out first, order of operations work until we get the variable in the exponent. Variable in the exponent, log both sides. So this is going to come into play because working with compound interest, working with interest equations, you're compounding over years. You're going to have that variable in the exponent. How long does something take? We're going to go with that. Now, I keep mentioning compound interest. Last year, maybe you remember, what was it, PERT? Yeah. We are not using PERT. Nothing base E. Do you remember what PERT gave you? We would say it was continuously compounded interest. Continuously. This class is discrete, not continuous. We are discrete, not continuous. So we're going to be using our compound interest, you've seen before, 1 plus r over n to the n t. Discrete, continuous. We are discrete math. No continuous. Okay. All right. Let's do another one. Oh no, there's stuff around. I'm just going to rewrite it so it shows up a little bit better. 4 to the 5t plus 64 equals 4250. Solving equation, working from the outside in. I notice variable in the exponent, we will take a log once we get rid of the outer pieces. So order of operations, reverse order of operations for solving, we'd subtract the 64. Now, the variable in the exponent is that outermost piece that we're trying to isolate. Now, technically, the outermost piece is the base 4. We need to eliminate the base 4. We do that by taking a logarithm. So variable in the exponent, log both sides. That gives us log 4 to the 5t equals log 4186. Just log of both sides. Exponent inside a log comes out front, turns into multiplication. So that's 5t times log 4. That's just going to be some number. Equals log 4186. Just some number. So I can evaluate, let's log 4, 0.602. So this is 5 multiplied by t multiplied by that value, 0.6021. Log of that. So it's multiplication, multiplication. We divide to get t by itself. So it's going to turn into t 3.622. I'm going to divide by the 5. I'm going to divide by that 0.6021. Now I can do this separately. I can do it together. If I'm doing this together, just make certain in the calculator that you bracket off everything by which you divide. Otherwise, it's going to divide by one and multiply by the other. Order of operations, be careful with the calculator. How's that look? Everybody loves logs? It's just a tool to get a variable out of the exponent for us. All right, one more. There's a whole bunch of stuff. I'm going to rewrite it so it shows up a little bit better. Reverse order of operations to isolate the variable. When we've got division, that serves as like bracketing, so there's the entire top, the numerator, divided by 0.004. We're dividing by 0.004, we'll multiply by 0.004. So I've got 54.73 multiplied by 0.004 gets us, it'll be 1 minus 1.004 to the negative 12t. Just getting that in. Moving over my head, I've got that variable in the exponent. Variable in the exponent, it's going to be a log. Well, working for the outside in, there's that 1. Subtract 1. So at this point, all right, variable up in the exponent. If we log both sides, and I'm doing something wrong, I know I'm doing something wrong. I'm going to correct it in a moment. Well, that's just some number, log negative 0.78108. If we plop that into the calculator, log negative 0.78108. Calculator, uh-oh. Non-real answer. Remember how much fun we had with imaginary numbers last year? Yeah. Do you want to use imaginary logarithms? We can define them. It's a whole lot of fun. It's really cool graphically, but we're talking money. You cannot have imaginary something with money. Well, you can have imaginary money. We're not handing out monopoly money in your bank account instead. The problem is the domain of a logarithm. The domain of a logarithm have to be positive numbers. Well, that's a negative number. We cannot take a log of a negative. I'm going to go a step back. Notice we've got negative equals a negative. Negative equals a negative. We can multiply by -1. Those become positive there. That fixes it. Log positive. Make it positive. Multiply or divide by -1. Variable exponent inside the log comes out front as multiplication. That's -12t. That negative's okay because it's not a negative base, it's a negative exponent. I'm going to save my multiplication division until the end with a log. I'm multiplying by t, so I would divide by everything that's multiplying against t. I'm going to have log 78108 divide by all those pieces that are multiplying by the t. Reminder, we're dividing by all of that, so in the calculator, make certain that we bracket that off. So I can put all that together in at once, skips rounding error. And we can solve. So big thing out of that, reverse order of operations. We started off with that big mess. Clear everything away until we get the variable and the exponent. Negatives, multiply or divide by -1 to make everything positive. We cannot take a log of a negative. It will come up non-real answer, or we'll give you something odd. We don't want that right now. Stick around for a complex algebra course, but that's not for us. We work it down, we can solve.